On September 14, 2015, a historic date for astrophysics and modern science, two gravitational antennas from the LIGO project, Laser Interferometer Gravitational Wave Observatory, located on the two coasts of the United States, detected a gravitational wave for the first time. This detection not only confirmed one of the boldest predictions of Albert Einstein's theory of general relativity, formulated a century earlier, but also opened a new window to the universe, ushering in the era of gravitational astronomy. The gravitational wave detected was generated by the collision of two black holes, with masses 29 and 36 times that of the Sun, respectively. These two extremely massive objects, after orbiting each other at increasing speeds, merged into a single black hole with a mass of 62 solar masses. In this merging process, a quantity of mass equivalent to about 3 times that of the Sun was converted into pure energy and radiated into space in the form of gravitational waves. This mass-to-energy transformation followed Einstein's famous equation, demonstrating how powerful such a phenomenon can be. Gravitational waves are vibrations of spacetime, generated by extremely violent movements of massive objects like black holes or neutron stars. Unlike electromagnetic waves, such as visible light or radio waves, which propagate through space, gravitational waves deform the very fabric of spacetime, altering the distance between 2 points in space as they travel at the speed of light. This signal took over 1 billion years to reach us, carrying with it invaluable information about the mysteries of the cosmos. Had the same amount of energy been released as electromagnetic waves, the resulting flash would have been tens of times brighter than all the stars in the universe combined. However, gravitational waves are silent in terms of light and radio waves. They are disturbances that pass through space, invisible to the eye but detectable with extraordinarily sensitive instruments like laser interferometers. The official announcement of the discovery was made on February 11, 2016, and it was met with great enthusiasm by the scientific community. Just over a year later, in 2017, 3 key physicists from the LIGO Virgo project, Rainer Weiss, Barry Barish, and Kip Thorne, were awarded the Nobel Prize in Physics for their fundamental contribution to the discovery of gravitational waves. This discovery represented the last major experimental confirmation of Einstein's theory of general relativity, marking the conclusion of a long search that began more than a century earlier. But why did it take so long to detect these waves? And what exactly are gravitational waves? Let's explore these questions more deeply. One of the main limitations of Newton's gravitational theory is that, according to its laws, the information regarding the gravitational field generated by a mass seems to propagate instantly through space. Newton's famous equation for the law of universal gravitation, which describes the attraction between two bodies, does not include time. This means that if the Sun were to suddenly disappear, the gravitational force it exerts on Earth would vanish instantly. This would imply an instantaneous transmission of gravitational information over any distance, a concept we now know is incompatible with the laws of relativity. The revolution brought by Albert Einstein's theory of general relativity, published in 1915, introduced an entirely new vision of gravity. According to Einstein, gravity is not a force that propagates through space, but the result of the curvature of spacetime caused by the presence of mass and energy. Massive objects like stars and planets warp spacetime around them, and other bodies move along these warps. When the mass that generates this curvature moves or changes, the curvature of spacetime changes accordingly, but these changes do not propagate instantly. They spread as gravitational waves, traveling at the speed of light. Einstein hypothesized the existence of gravitational waves as early as 1916, shortly after completing his theory of general relativity. However, in the following decades, he often doubted their actual existence and especially the possibility of detecting them. Gravitational waves are extremely weak and difficult to measure, and even the most violent changes in spacetime produce minimal effects that diminish rapidly with distance. Gravitational waves behave very differently from familiar waves like sound waves or water waves. When a wave reaches an object floating on water, the object begins to oscillate up and down. In contrast, gravitational waves do not make objects oscillate, but instead distort spacetime itself. This means they alter the distance between 2 points in space and the duration of time intervals along their path. A simple way to visualize this effect is to imagine a sphere floating in space, like the Earth, being struck by a gravitational wave. As the wave passes through, the sphere is compressed in one direction perpendicular to the wave's propagation and then stretched in the opposite direction. This process of compression and stretching repeats cyclically until the wave weakens enough to no longer cause measurable deformations. Gravitational waves are generated by violent movements of enormous masses, such as the merging of black holes or neutron stars, and they propagate through spacetime at tremendous speeds. However, their intensity decreases rapidly with distance, making it extremely difficult to detect them from events occurring billions of light-years away. Even so, their detection provides us with unique information about phenomena that would otherwise be invisible, such as black hole mergers, which do not emit visible light or other forms of electromagnetic radiation. Detecting a gravitational wave requires extraordinarily sensitive instruments capable of measuring infinitesimal variations in the distances between 2 points in space. In the 1970s, physicists realized that a device called a laser interferometer could be the solution. The idea is to split a laser beam into 2 rays that travel along perpendicular arms and bounce off mirrors placed kilometers apart. Upon returning, the 2 beams of light recombine, and the tiny differences in their paths, caused by the passage of a gravitational wave, can be detected with extreme precision. The technological challenge to build these interferometers was enormous. Over the length of the interferometer's arms, spanning several kilometers, the variation caused by the passage of a gravitational wave is thousands of times smaller than the nucleus of an atom. However, after decades of refinement and technological development, in 2015, LIGO finally succeeded in detecting a gravitational wave, paving the way for a new era in science. The observation of gravitational waves not only confirmed the theory of general relativity but also inaugurated a new way of doing astronomy. Until recently, everything we knew about the universe came from electromagnetic waves: visible light, radio, infrared, X-rays, and gamma rays. Now, gravitational waves allow us to observe phenomena that do not emit electromagnetic radiation, such as black hole mergers. In 2017, a further step was taken with the simultaneous detection of gravitational waves and electromagnetic waves from the merger of 2 neutron stars. This combined observation marked the beginning of multi-messenger astronomy, an approach that provides us with a more complete and detailed view of cosmic phenomena. Gravitational waves allow us to observe events that would be invisible to traditional instruments and provide us with information about the structure of spacetime, the distribution of mass in the universe, and the dynamics of extremely dense and compact objects. This is just the beginning. In the coming years, with the advent of new and more powerful detectors, such as LISA, we will be able to explore the universe in ways previously unimaginable. Thank you for watching. Leave a like and subscribe to the channel.